My name is Katrina Keleher. I'm a graduate student at the Evergreen State College. Today I'm going to be talking about my thesis research on microclimate spatial variability on the Olympic Peninsula. I worked on this project with Warren Devine and Richard Bigley, both of DNR. So to begin, I'm going to give you a brief overview of what riparian areas are and why microclimate is an important component of them. Riparian areas are the interface between land and a stream or a river, and they're important for a variety of reasons. They support the highest biodiversity in forested areas due to their abundant moisture and high productivity. They stabilize stream banks and control erosion in doing so. They regulate water temperature and light regimes. They filter nutrients and pollutants from the uplands, and all at the same time, they're providing food, shelter, and water for wildlife and a variety of plant species. So preserving vegetated strips of land was first applied in the US in the 1960s, and the Washington Forest Practices Act was adopted in Washington State in the 1970s and expanded upon with the Timber, Fish, and Wildlife Agreement in the 80s. And that agreement introduced a range of riparian management rules into the act. And the OESF-specific riparian buffer practices were outlined in DNR's Habitat Conservation Plan's Riparian Conservation Strategy. Currently, streams in the OESF have a 100 or 150 foot unharvested buffer on either side of the stream. So an important part of riparian areas and riparian buffers is microclimate. Microclimate is a local set of climatic conditions for a really small area, and it includes a suite of variables like temperature, moisture, humidity, wind speed, and light. And microclimate is vital for the functioning of a variety of systems and processes in riparian areas, including decomposition, nutrient cycling, ecological succession, vegetation production, and habitat suitability for a suite of plant and wildlife organisms. And a lot of species require a specific set of attributes in order to survive, and microclimate is one of those. So we began this study looking at a number of research questions. They include, how does microclimate vary spatially within and across the riparian transects in the OESF? What topographic and vegetation factors explain that variation? And what are the ecological drivers of riparian microclimate? So this study took place on the OESF, and Teddy did a good job outlining what that is and why it's important earlier this morning. But just as a reminder, it's an area that contains 270,000 acres of state trust forest lands. And the objective of the OESF is to produce revenue for state trust land beneficiaries like schools and hospitals through timber harvesting, while simultaneously managing for ecological values. So the status and trends monitoring of riparian and aquatic habitat is a project that's been taking place on the OESF since 2012. And this project is looking at the longer-term influence of DNR's management practices on aquatic and riparian habitat. The hypothesis of the project is that current riparian protections are maintaining ecological processes and resiliency. One of the components of this bigger project is riparian microclimate, and that's what I'm talking about today. So microclimate stations were installed in 10 of the 50 Type 3 watersheds included in the OESF study, and they were installed in transects on either side of a stream in each basin, extending from the stream 60 meters away from the stream. These microclimate stations recorded air temperature and humidity every 2 hours for the duration of the study, which was 3 years, 2014, 2015, and 2016. So as you can probably imagine, that was a lot of data to work with. This is what one of the microclimate stations looks like. That's a Hobo V2 Pro logger that's mounted on a U-post. and there's a protective housing on top of it, which is just a bucket. So this past summer in 2018, Richard, Warren, and I went out into the OESF. We traveled to all 10 of the basins included in this study and hiked all 20 of the transects. We did this to make sure that we knew exactly where all of the microclimate stations were located, and this came in handy for analysis later on, which I'll talk about soon. So for this study, we created mixed multivariate models using 3 dependent variables as our inputs. We looked at mean daily maximum summer temperature. We looked at mean daily maximum summer vapor pressure deficit, and we also looked at cumulative degree days. We decided to include this last variable in the study to examine a metric other than just maximum temperature or vapor pressure deficit. Cumulative degree days is a way to look at air temperature over a 24-hour time period. So as I've been working on this project for the last several months, I've found that many science-minded people don't know what vapor pressure deficit is, so I wanted to include this slide to clarify that. It's a metric that explains how dry, what the drying power of the air is, and it's calculated by subtracting the actual vapor pressure of the air from saturated vapor pressure. We decided to look at this metric instead of relative humidity because it's more biologically significant since its value is independent from air temperature, whereas relative humidity is not. And if this helps you think about it a little bit better, when vapor pressure deficit, when the value is 0 kilopascals, relative humidity is at 100%, so they're inversely related. These are 3 plots showing some of the variation we had for the dependent variables throughout the duration of the study. I know that the axes titles are kind of small, but on the left we have a plot showing temperature over the 3 years. In the middle we have vapor pressure deficit over the 3 years, and on the right we have degree days. As you can see, there is quite a bit of variation across the years. For those of you that lived in Washington in 2015 or in Oregon in this region, you might remember that it was a particularly dry and warm year. And I'm really happy that that year was represented in this study because, as we know, these unusually warm and dry years are becoming more and more of the norm as the climate continues to change. This is a plot showing some of the variation we saw across the transects. This is for temperature. This is for vapor pressure deficit. And here we have cumulative degree days. So there was a lot of variation across all 20 transects included in this study. So in addition to those dependent variables, we looked at a number of fixed predictor variables, including distance from stream, height above stream, percent canopy closure, and solar radiation. And just so you know, as I continue to progress throughout this talk, I might refer to distance from and height above stream as just distance and height, but just keep in mind that I'm referring to those variables based on their location from the stream. So let's focus on those 2 variables first. This is a plot showing some of the variation we had across the sites in terms of topographical changes. Some of the sites were relatively flat from the stream extending into the forest. Others were quite steep, and Warren and Richard and I think can all attest to that. So this is interesting to think about because a lot of people think of riparian areas as linear things and being relatively flat. In reality, especially out here, that's not the case. These are 3D renderings of all 10 of the basins. I wanted to include these in this presentation just to show you what this topographical variation looks like. Let's take a closer look at 2 of these basins. So we have basin 724 on the right and basin 642 on the left. These demonstrate a pretty steep basin on the right and a pretty flat basin on the left. So these tiny red dots, you might not see them well in the back, but these represent the microclimate stations, and they're located on their transects on either side of the stream. And this basin was quite steep, whereas this basin, especially this transect on the right side of the stream, was relatively flat. But I also wanted to point out that in this same basin, we have this second transect that begins flat and then ends up getting quite steep. So not only did we see topographical variation across the basins, but we also saw variation within the basins. This is what that all looks like on the ground. I want to direct your attention to this middle picture in particular. I took this standing from the stream, and that little yellow thing on the top is Richard. He's behind a tree, so he's hard to see. But he's walking to one of the microclimate stations. So right off the bat, this site was very, very steep, and we couldn't just walk to the stations. We had to scramble and climb. So we also looked at percent canopy closure. Percent canopy closure was calculated from hemispherical photos that were taken by DNR technicians in 2014 as part of vegetation surveys. And the photos were then processed using a software called Hemisphere. DNR staff then calculated percent shade by counting the black pixels present in each image. So we had shade closure data for every single microclimate station included in this study. So we also looked at solar radiation. This is different than canopy closure because it wasn't looking at vegetation attributes the way that was. And this is where our fieldwork over the summer really came in handy in terms of knowing exactly where the microclimate stations were located, because we were able to calculate the incoming solar radiation for each of those stations using a tool on ArcGIS called the Area Solar Radiation Tool. This tool was overlaid on a digital elevation model and calculated the amount of solar radiation received at each raster pixel. This is just an output zoomed out at one of the basins included in this study. And you can see that in terms of the color ramp I used here, the darker the color, the less solar radiation was received at that site. So this tool took into account slope and aspect and other attributes. Before I get into the results of the multivariate models that we made, I wanted to point out that distance from stream and height above stream were found to be highly correlated. Because of this, I decided to drop the weaker of the two variables from the models, and that was distance for every single model. So here's the output table for the mean maximum air temperature multivariate model that we created. We found that height above stream and solar radiation were good predictors of mean maximum air temperature. This is what that looks like in a 3D plot. We have maximum air temperature on the y-axis and solar exposure and height above stream down here. And how you read this plot is if you look at solar exposure when it's at its highest, you follow that up the plot and see that this is how good of an effect it has on temperature. And this is telling us that solar exposure for temperature was found to be a better predictor than height above stream was. We also made a mixed multivariate model for vapor pressure deficit. We found similar results that height above stream and solar exposure were good predictors for this variable. Here's the 3D plot for that. And height above stream was actually found to be a little bit of a better predictor for VPD than solar exposure was. And finally, here's the output table for the cumulative degree day analysis. We found that height above stream was found to be a good predictor for cumulative degree days. I still included solar exposure on the 3D plot, mainly because 3D plots are cooler than 2D plots, but also because this way it shows you how good of an effect height was on cumulative degree days. So the closer to purple you get, the better the effect. And it took some pondering to think about why solar exposure was not found to be a good predictor for degree days like it was for VPD and max temperature. And we think that it has to do with the fact that to calculate degree days, you do it over a 24-hour time period, and the sun is not up for that entire duration, whereas for the maximum temperature and vapor pressure deficit values, the sun was likely shining directly overhead, as those values probably took place in the afternoon heat. So to conclude, we found a few key findings. We found that solar exposure was a good predictor for air temperature and vapor pressure deficit. We found that height above stream was a good predictor for microclimate variables in all models that we examined. And perhaps the most interesting finding was that height above stream was found to be a better predictor for microclimate variables than distance from stream. This is really interesting when you think about how riparian management zones are designated. They're designated for the most part from distance from stream. That leads me into management implications. So moving forward, I think that land managers should try to, if possible, consider height above stream when they are designated riparian management zones. Although it's important to consider that even though height above stream was consistently a better predictor for microclimate in this study, distance also was a good predictor, and it's still important to consider for other riparian values when you're designating riparian buffers, primarily for habitat preservation. In terms of future research, it would be great if future research on riparian microclimate looked at this relationship between height above stream and microclimate gradients in riparian management zones. It would also be interesting for future research to explore other spatial variations, either in the same location in the OESF or in other locations in the Pacific Northwest, using other metrics as opposed to just maximum temperature values and vapor pressure deficit values. And finally, it would be great to see research looking at the influence of adjacent timber harvesting on microclimate gradients, and maybe that will happen on the OESF in the future. That's me. Thank you to all these people on the screen, to Richard, Warren, and Teddy, all of DNR. Thanks to Kevin Francis, he's my thesis reader at Evergreen, and thanks to the Master of Environmental Studies at Evergreen as well. Thanks.